Everyone, I'm Mohamad Chaarawi. I'm from HPE. We are here at Argonne today doing a hackathon with a few folks. See quite me and John and Gordon in the room. So today I'll present some best practices and performance and tunings that we've seen while working on Aurora and other systems. And that the idea of this talk is to just go quickly through some preferred settings we found for containers, what to use for objects, and specifically on erasure coding, because we find that it gets pretty complicated to get things right the first time always. And if there's time permit, I'll talk a little bit about different ways to access POSIX containers and some common issues that come up with each of those ways. So first of all, containers. When you create containers, a common question is that what redundancy factor to use. So the first thing before to understand that is that you need to understand what is a fault domain on a DAOS system. A fault domain is a unit of failure. It actually can be set on pool creation or on container creation. But for the sake of this talk, let's think of a fault domain as an entire server node. But technically, it can be a single SSD, it can be an engine, it can be the server, it can be entire rack of server connected to a switch. By default today, as I said, the fault domain is set to the DAOS server node, and let's consider that for our talk today. So when creating a container, if you care about your data, you're not doing just checking capabilities of your system or something like that, you should always remember to set the redundancy factor on the container. Today, it's not default unless you set it on the pool. So if you don't set the redundancy factor on the pool, by default, your containers will be created with no redundancy, and you have to remember to set it to 1 or 2 or whatever number of fault domains you want to tolerate failing concurrently. So setting it to 2 means you can lose 2 server and still have data rebuild and maintain the data integrity, data integrity in your container in that case. And once data is rebuilt, you're fine. Your container becomes is healthy, not more in an integrated state. You can lose more, another 2, and so on, as long as rebuild completes. So yeah, that's one thing users need to make sure they're using unless it's set on the pool. And if you don't use proper redundancy setting, if some of the engines or SSDs are lost due to different issues, you will experience data loss or data corruption in your files in that case. Second are checksums. Checksums are a way to provide end-to-end data integrity when using DAOS. Basically, once you give data to DAOS or you are reading data from DAOS, using checksums ensures that data stays intact as soon as you hand your buffer to DAOS and until it's on SSD or the other way around. So if there's like a possibility of corruptions on the network side or as data is transferred or some other places, checksums will ensure that if you're writing, your data stays intact. There's no silent data corruption as you are moving the data through the stack, right, through the network. And we've seen some network providers or settings sometimes there's data corruption introduced in that case. And on the write, for example, if DAOS detects a checksum error, it will redo the write until there's no checksum error. So there's different checksum types supported, and the important thing is to set it on container creation. It's not default, but we've had discussions that really we should make it default in the future. Performance wise, we've seen very minimal overhead when using checksums. especially if you're looking at single process performance, you can see, I would say, about 10 to 15% performance degradation. But in theory, bandwidth or IOPS wise, when you have a lot of more than one thread doing IO, that performance degradation becomes negligible in that case. So now for talking about object classes, when you create objects. So as you know, at the lower level, DAOS is a KB store, basically, or key array store, basically. You have put the DFS layer, files, directories are built on top of the low-level API. And objects can be created with different redundancy types and levels depending on your redundancy factor you set on the container. So you can create objects with no redundancy, meaning your data is just written in one place with no replication, no erasure coding, and of course that's not recommended for use in any production setting. There's a replication. There's a replication schema where it's always good for very small IO, very small files, or small objects, basically, or metadata objects like directories in the POSIX world. It's good to use replication for that because erasure coding won't buy you much. It's actually counterintuitive to use erasure coding for small objects and metadata objects, and erasure coding, which is good for files generally that are medium to large size, and that's where best to use erasure coding. By default, DAOS uses erasure coding for files and replication for directories. We'll talk a little more about the specific object classes in the next slide or so, but depending on what the redundancy factor on the container, you can see for file, it's either no redundancy but widely striped. For directories, it's single target and single target and no redundancy. Replication for directories, erasure coding for files. On the container create, if you can modify the file and the directory object class when you're creating POSIX container. The default settings are immutable, but you can of course change the object class for files and directories other than the default if desired once after you create the container. But today you cannot change the actual default on the container for files and object classes. And the default usually works fine in most scenarios, but sometimes, like if you have tiny files, it's not really the ideal scenario. It'll still work, but performance will not be great and it's better to change that for those specific files in such scenarios. So in terms of what it means when to set redundancy and some considerations you want to take. For erasure coding, as I said, it's best when you have large files and large IO access patterns to match. And we'll talk about. I have some performance numbers to share what I mean here. By full stripe and partial stripe updates, depending on what type of IO you're doing and what's the erasure code class and what's the cell size and all of that. As I said, prefaced in the beginning, it's complicated, but how to get it right. But you can see that the performance hit can range between 12% and 60%. So for write, of course, for read it should be the same. Erasure coding is not supported for directory objects. You can try to set it, but I cannot guarantee good results. So yeah, for that, a replication, which is best for metadata objects and small files. IOPS is slower. I mean, write IOPS, depending on how much replication you're doing. If it's two-way replication, you're gonna get half the IOPS, half the bandwidth. Read IOPS will be the same. Actually, read IOPS can be better because you have more concurrent shards to serve those reads. In terms of sharding or striping, as you probably know, I mean, it's common to other file systems also. You can either have widely striped or small striped object. Widely striped means your data is striped over all the targets on your system. That's what we say by X here. That's means widely striped. So that's always best for getting the max bandwidth for your IO. most IOPS, if you have like a very dense directory, for example, if you're doing file per process, your files are not very large. That's not the ideal setting. And why is that? If you have like a lot of files and you do something like ls on your directory, what we're doing is that we need to stat every file, and to stat every file, we need to go to talk to every engine in your system to grab all the metadata on that file to know the size of the file. And if your system is small, it doesn't matter. If your system is large, I'm talking about the DAOS system basically. If you have a lot of servers, a lot of targets, that can be quite expensive compared to small striped objects. Similarly, with removing the file, it's also more expensive for widely striped objects than it's for small striped objects. For stat and things like that, if you have diffuse caching works, but caching in diffuse is limited to single node or read-only scenarios, which not always the case. Small striped objects are good if your file, as I said, your files are small. It limits the bandwidth to the number of stripes or number of shards you are using. 1, 2, 4, 16, 32. Those are the pre-coded ones in DAOS. We probably thought about adding more, because some larger systems can use larger targets. In that case, you get limited bandwidth. Of course, if you are writing more than what your stripes can fit, you can get Eno space. So it's important to understand that. Your metadata operations will be fast in this case. So you get fast ls, fast remove, because it's a limited number of targets per file that you are doing. So recommendations for object class. If your files are large, are talking about RF0, RF1, RF2, but let's talk only about RF2. Use EC. 16p2 is if you have a large system that can support 16p2, but you can do like 8p2, 4p2, and so on, and use GX in that case. If the files are tiny, where we're talking tiny, but we're talking on the order of bytes or kilobytes, basically, it's better to use G1. It's actually better not to use EC, just use replication in that case. To avoid the complexity of EC, because in the sense EC will be doing replication for these tiny files. And if there's something in between, you use the other striping parameters that you have. Still, you keep using EC for files. Again, 16p2, 8p2, 4p2, 2p2, but don't use GX, don't use G1, use like G32, G16, something that's better suited for such files. The way to change object class for files and directories, we can either if you set something on your container but you want to change it for some files or some directories. If you're using DFS, you can use the API. That's fine. That's not always the case. Not many users use the DFS API directly. Use MPI.io, for example. There are info hints that you can do. Or you can use the DAOS tool to create a directory and set the object class for everything created under that directory. Now, if you cannot separate files in different directories, use the default. It's not ideal, but it will be the best setting in that case. So last thing, since I'm not gonna have a lot of time, last thing I will talk about is some performance number with EC. So with EC, there's a lot of parameters you need to that comes into play to get the best performance. There's the EC object class, 16p2, 8p2, 4p2. There's the cell size. By default, it's 64K, but we actually find 128K is more appropriate, so we might change that in the future. And next release, we'll see. The DFS chunk size, basically how much you put under, or we can call it stripe size, how much you put under a certain D key. If you're using 16p2 and your cell size is 128, using the default 1 megabyte is actually going to get you into partial stripe updates all the time, because 128K times 16, that's 2 megabytes. So anything under 2 megabytes would be a partial stripe update. So you want to set the DFS chunk size in this case to at least 2 megabyte. 4 megabyte is even better. So that just setting these default settings is good to get performance, but that doesn't mean others are is not supported, right? It's just not performance well. So to give an example of performance, here I'm showing some results we've gathered on Aurora for varying the EC cell size, basically, the one that you set for the EC on the container. We're using 16p2GX for this. We have single shared file, and you're doing 128, 256, 512 struct size. Let's take 128, for example, first, and looking at the DFS chunk size and the IOR transfer size. If we're doing 128 and 16p2, the point where we do partial stripe update is under 2 megabyte, and the point we're doing more than we were doing full stripe updates is more than 2 megabyte. So you can see everything here is pretty low, but as soon as we go from 1 megabyte to 2 megabyte and higher, you see this big jump in performance, going from partial stripe to full stripe updates. Similarly, for 250, if you set your cell size to 256K, and since you're using 2p2, now 4 megabyte is your breakpoint, basically going from partial stripe to full stripe. So you can see your for 256, your performance is low until 2 megabytes. 4 megabyte, you get this big jump going from partial stripe to full stripe updates, and same for 512K EC cell size. 8 megabyte is the breakpoint. You know, anything under 8 megabyte is low. 8 megabyte and higher is high. So that's something to take into consideration always when doing EC and to get the best performance. So since I have 15 minutes only, I won't roll over. I'll stop here and maybe take some question.
Thanks, Mohamad. Questions for